Welcome, curious minds, to another deep dive into the unseen forces shaping our world. Today, we're pulling back the curtain on something incredibly complex, yet absolutely critical to your everyday safety.
Yeah, we're talking about the software inside your car.
Exactly, the intricate dance of software happening inside your car. It's the unseen guardian, constantly working to keep you safe.
That's right. We're embarking on a crucial deep dive into ISO26262. Specifically, it's Part 6, product development at the software level. As vehicles become more and more software-defined, this standard is essentially the automotive industry's functional safety playbook.
And software is right at its core.
At its absolute core. It's where those abstract safety goals become actual lines of code that protect us.
And that's really our mission for today. We want to explore exactly how automotive software is designed, developed, and then, crucially, rigorously tested to prevent and mitigate hazards in road vehicles.
Yeah, we'll unpack the specific activities, the core purposes, and the paramount importance of each step in this incredibly intricate process.
So by the end of this, you should have a really solid understanding of how those high-level safety requirements actually transform into executable code.
Exactly. And how software architecture is built for resilience against faults, and the multi-layered testing strategies that ensure robust, reliable, and ultimately safe software.
Get ready for some fascinating insights then. Maybe even a few surprising facts about the engineering behind the automotive safety we often just take for granted.
Definitely. It's quite a world.
Okay, let's unpack this. First, maybe we should ground ourselves in the overall structure of automotive functional safety. As many of you might know, the ISO 26262 series of standards, which Part 6 is, part of, it adheres strongly to what's famously known as the V model.
Right, the V model.
Yeah.
Think of it like a journey, yeah. From abstract requirements down to concrete implementation.
And then back up the other side.
Exactly, back up through rigorous verification and validation. It's a foundational reference process for product development in this field.
And what's truly fascinating here is how Part 6 slots into that V model. Where does it fit?
Well, it resides firmly on the right side of the V. This isn't about the initial hazard analysis or, high-level concept creation.
Right, that's earlier stuff.
Those critical steps are handled in earlier parts of the standard, like ISO 26262-3 for hazard analysis and risk assessment, and ISO 26262-4 for system-level development.
Yeah.
Part 6 is really where the rubber meets the road for software. It zeroes in on the crucial development and verification phases, specifically for the software itself.
So how the code gets written and checked.
Meticulously detailing how the software itself is developed and then rigorously checked, all while deeply intertwined with parallel hardware and system development efforts. It's the point where, theoretical safety becomes practical reality.
And it's really important to grasp that not all software in a car needs the same level of safety rigor, right?
Yeah.
This is where ASIL automotive safety integrity levels come in. Could you shed more light on how ASILs dictate the intensity of these processes? What does that mean in practice?
Absolutely. ASILs are, they're the bedrock of ISO 26262. They're assigned based on a thorough analysis of three factors. The potential severity of harm if a hazardous event occurs.
How bad could it be?
Exactly. Then the exposure probability to that hazardous event.
How often might it happen?
Right. And finally, the controllability by the driver or other means. Can the driver prevent the harm?
Okay. Severity, exposure, controllability.
And based on those, you get an ASIL, from A up to D, D being the most stringent. The higher the ASIL, the more rigorous the requirements and recommendations become for every single activity within the standard.
So ASIL D means you pull out all the stops.
Pretty much. Consider this, a function like the software controlling your anti-lock braking system, where failure could directly lead to loss of control and severe injury. That would likely be ASIL D.
Makes sense. High risk.
Which means every single step of its software development, from the fundamental design principles it adheres to the depth of testing coverage, to the qualification of the tools used to build it, will demand the highest level of detail, evidence, and independent verification. It's about minimizing the residual risk to an absolutely acceptable level.
So an ASIL D component is under incredible scrutiny. What about something less critical?
Well, conversely, a less critical function, maybe related to a non-safety critical display element, might be ASIL A, or even QM, quality management.
QM.
Quality management. It still requires proper development and quality assurance, of course, but the specific methods and the depth of proof wouldn't be as exhaustive as for ASIL D. This ASIL dependency, outlined in Clause 4.4, is what makes the standard scalable and frankly, pragmatic.
Yeah, otherwise it would be overkill for everything.
Exactly. It allows engineers to focus their most intense efforts where the safety risk is highest. It's a smart allocation of resources to maximize safety.
Okay, so if software development is on the right side of the V, it means it's inherently building upon earlier work done at the system level. How exactly does Part 6 pick up from what happened upstream, particularly from system-level development described in ISO 26262-Part? It sounds like a crucial, almost sacred handover of information.
It truly is a crucial handover, and you've hit on the right word. Sacred. The software development phase described in ISO 26262-6 isn't an isolated activity. It's a direct, logical continuation of earlier stages, especially the system-level development detailed in ISO 26262-Part.
So it relies heavily on the inputs from Part 4.
Absolutely. The vital inputs received from these upstream phases are the technical safety concept, or TSC, and the system safety requirements, or SSRs. These aren't just dry documents. They are the high-level directives that encapsulate the overall safety strategy for the entire vehicle system. They articulate what the system must do to be safe.
Okay, so we're talking about translating these, well, fairly abstract concepts into something concrete and executable for the software. That sounds like a monumental task, almost like taking a grand architectural vision and turning it into precise blueprints for every pipe and wire.
That's a good analogy.
What's the core objective of this transformation, and what's the biggest challenge?
The core objective is precisely that: to meticulously transform and refine these abstract, system-level requirements and safety concepts into executable, safety-critical software code. This is where the theoretical aspects of safety begin to take concrete, implementable form, line by line.
Turning what's into how for the software.
Exactly. Imagine the TSC outlines a broad safety goal, like the vehicle must safely avoid imminent collisions. The system safety requirements, the SSRs, then break this down into more actionable directives, like the system shall detect obstacles within X meters using radar, or the system shall apply Y braking force if a collision is unavoidable.
Okay, more specific.
Right. The biggest challenge, and the focus of Part 6, is taking these detailed system requirements and translating them into the specific software logic that performs radar data processing, calculates precise braking force, manages communication with actuators, and robustly handles potential errors.
Wow.
This entire chain, from high-level idea to precise code, must maintain its safety integrity at every single step, ensuring that nothing is lost in translation and, importantly, no new hazards are introduced. It's about ensuring the software faithfully executes the safety intent.
That makes perfect sense. Now, once we have that foundational understanding, the next critical stage is defining the software-specific safety blueprint. This involves the specification of software safety requirements, or SFRs. What's the primary objective here, and how do we go about deriving these requirements from the system level?
Okay, so the primary objective, as outlined in the standard, is to specify or refine the software safety requirements, the SFRs. This means taking the system's overall safety goals and meticulously breaking them down into specific responsibilities that the software itself must fulfill.
Right, drilling down from system to software.
It's about moving from what the overall system must do for safety to what the software specifically must do and how it must behave to achieve that safety.
And what exactly do these SFRs define? Are we just talking about the functions the software performs, or is it, something deeper?
It's definitely deeper. SFRs define both the safety-related functionalities, what the software does, and crucially, the properties, what the software is, and how it behaves that it must possess to achieve functional safety.
Functionalities and properties. Okay.
It's not just about turning the wheels or reading a sensor. It's about doing so reliably, predictably, and robustly, especially when things inevitably go wrong.
Could you give us some concrete examples of these safety-related functionalities? What kind of specific actions or operations are we talking about here that are directly tied to safety?
Certainly. The standard provides excellent illustrations. For instance, you have functions that enable the safe execution of a nominal operation, like ensuring the cruise control system maintains a safe speed and gracefully disengages under certain conditions.
Okay, normal safe operation.
Then there are functions that help the system achieve or maintain a safe state, or even a degraded operational state. Think of a limp home mode.
Yes, I've heard of that.
If a critical engine fault is detected, the software intelligently transitions the vehicle to a minimal, safe operational capacity, allowing you, hopefully, to get to a service center without catastrophic failure.
Very important function.
We also consider self-test or monitoring functions. This is where the software actively checks itself or related hardware for faults.
Mm.
An example is a watchdog timer.
A watchdog.
Yeah, it's essentially a critical software component that constantly monitors if another vital process is still running and responding. If that process stops responding, the watchdog can trigger a reset or transition to a safe state, preventing a potential deadlock or, uncontrolled behavior.
That sounds like a lot of internal checks. What about interactions with the outside world or during the car's entire life cycle?
Precisely. SFRs also cover functions related to onboard and off-board diagnostics and tests, both during vehicle production and throughout its service life. This ensures the software can be properly verified, updated, and maintained over potentially decades.
Right, long life cycles.
And importantly, there are functions for safe modifications of software during production and service. Imagine a secure over-the-air update system.
OTA updates, yeah.
The software itself must guarantee the integrity and safety of the update process to prevent malicious or accidental corruption. That's a huge area now.
Absolutely.
Lastly, any time-critical operations, like the rapid response of an airbag deployment system or the precise timing required for an anti-lock braking system, would have their timing constraints meticulously defined as safety-related functionalities within the software requirements. Every millisecond counts here for safety.
It's clear that functionality is key, but you also mentioned safety-related properties. What kind of non-functional properties are important for software safety? They sound just as critical.
They are equally critical, yes. A prime example is robustness against erroneous inputs. What happens if a sensor sends a wildly incorrect value, say a wheel speed sensor, suddenly reports a negative speed while driving forward?
Yeah, that shouldn't happen, but what if it does?
The software needs to be robust enough not to crash, produce an unsafe output, or cause a hazardous state. It might achieve this by filtering the input, using plausible ranges, or defaulting to a safe assumption. This prevents a single faulty input from derailing the entire safety system.
Okay, handling bad data gracefully.
Then there's independence or freedom from interference between different software functionalities. This is huge and often surprising to people outside this field. Imagine your critical braking software running on the same microcontroller as your non-safety-related infotainment software. A bug in the infotainment system, like a memory leak, cannot be allowed to affect the braking software. The standard requires rigorous design and verification to ensure this independence, preventing seemingly benign faults from cascading into critical safety failures.
Wow, that's a crucial firewall.
It really is. And finally, fault tolerance capabilities, meaning the software's ability to continue operating safely even in the presence of faults, perhaps by using redundant computations or sophisticated error-correcting codes to self-heal or degrade gracefully.
These sound like very detailed considerations. What other crucial factors are considered during this SFR specification phase to ensure robust definitions?
There are several crucial factors, yeah. First, the SFRs must intricately consider the system and hardware configurations. This means understanding how the software needs to adapt to specific hardware parameters, like the exact gain control settings for an analog-to-digital converter, the band pass frequencies for a signal processing unit, or the clock prescalers that determine timing on a microcontroller.
So it's very hardware specific.
The software isn't just a generic piece of code. It's intimately tied to the specific silicon it runs on.
Okay, what else?
Second, the hardware-software interface, HSI specification, is absolutely critical. This document, which is actually initiated at the system level, is refined here to ensure correct and safe control of hardware by software. It meticulously outlines every safety-related dependency and interaction between the two.
Like the handshake protocol.
Think of it as the precise, non-negotiable handshake protocol between the brain, software, and the body, hardware of the system. Any ambiguity here is a potential safety loophole.
So it's not just about what the software does internally, but how it interacts perfectly with its physical environment. What about performance or timing?
Absolutely critical. Third, timing constraints are paramount. The software must adhere to strict timing requirements such as execution times for critical functions and reaction times to external events. These are derived directly from system-level response needs.
Like that 100-millisecond braking example.
Exactly. If a safety function needs to detect an obstacle and initiate braking within, say, 100 milliseconds, the SFRs must define that the software executing that function has to meet that exact deadline under all operating conditions. Missing a deadline can be just as dangerous as a functional error.
Makes sense.
Fourth, external interfaces must be considered. This covers how the software interacts safely with other systems in the vehicle. for example, via vehicle networks like CAN or Ethernet, or with user interfaces, ensuring that no unsafe commands or data can be passed to or from the system.
Protecting the boundaries.
And finally, and quite comprehensively, vehicle operating modes. SFRs must account for all vehicle states, from initial power-up and diagnostics to normal operation, degraded modes, emergency states, and even advanced testing or programming modes. Each mode might have unique safety requirements, requiring specific software behaviors to maintain safety. It's a truly comprehensive approach.
All these definitions sound incredibly complex, so the process of verifying them must be equally rigorous. How is that handled for SFRs before you even write code?
The verification process for SFRs is indeed rigorous, and yes, it happens even before coding begins. It's about ensuring these requirements are suitable for software development, consistent with the overall technical safety concept, compliant with the system design, and consistent with the HSI.
How do you do that?
It involves techniques like formal reviews, inspections, and traceability analysis to ensure every safety goal from the system level has been correctly, unambiguously, and completely translated into a software requirement. This meticulous cross-referencing and verification are essential to catch errors early.
Because an error in the requirement is bad news later on.
Exactly. A fault in a requirement can propagate throughout the entire development cycle, becoming exponentially more expensive and dangerous to fix later on. Catching them here is key.
Amazing. Now, we've specified the software safety requirements. The next logical step is to build the actual structure, the blueprint, the software. Let's move on to architecting for safety. The software architectural design. What's the core objective of this phase, and what exactly does a software architectural design entail?
Right, the architecture. The core objective here is to develop a software architectural design that meticulously satisfies all the derived software safety requirements and any other software needs. It's the foundational blueprint, similar to how an architect designs a building before any bricks are laid.
So the high-level plan.
What it entails is a hierarchical structure of software architectural elements and their interactions. This isn't just about what the code does, it's about how it's organized, how its components interact, and how it's structured to ensure safety, robustness, and maintainability.
So is this just a static diagram like boxes and arrows, or does it also include dynamic aspects like how the software actually behaves over time?
It's definitely both. The design distinguishes between static aspects, such as the fixed interfaces between software components, the data types they exchange, or the memory layout.
The structure.
But it also defines crucial dynamic aspects, such as process sequences, the exact execution order of tasks, and their timing behavior. For example, a static aspect might define that the brake control module interfaces with the wheel speed sensor module via a specific data bus and uses a certain data structure for speed. A dynamic aspect would then precisely describe the sequence. How often the brake module requests wheel speed data, how quickly it processes it when it sends commands to the actuators, and what happens during different operating states like power-up or normal operation.
That makes perfect sense. Now, designing for safety means proactively avoiding problems from the start. What are the key design characteristics and underlying principles that this architectural design must exhibit to ensure robustness and prevent those dreaded systematic faults?
Yeah, avoiding systematic faults, those errors introduced during design or development, is the name of the game here. The architectural design must exhibit several essential characteristics. We're talking about comprehensibility,
easy to understand,
consistency, ensuring all parts align, simplicity, avoiding unnecessary complexity, verifiability so it can be rigorously checked, modularity, breaking it into manageable pieces.
Modularity seems key.
Oh, definitely. Abstraction, using hierarchical structures to manage detail. Encapsulation, containing functions and data within defined boundaries to limit side effects. And maintainability, making it easy to update or fix without introducing new risks. These characteristics are fundamental.
So these are the guiding stars for a good design. But what about practical principles for actually preventing systematic faults, like rules of thumb or established best practices engineers follow?
Absolutely. These principles are vital for building a robust and safe architecture. One foundational principle is an appropriate hierarchical structure. Think of it like organizing a massive library. You don't just dump all the books in one pile. You categorize them, put them on shelves, organize them into rooms.
Makes sense, avoids chaos.
This layered approach prevents spaghetti code and makes the system understandable and manageable.
Okay, what else?
Another crucial principle is restricted size and complexity of software components. Keep individual modules small and focused. This makes them far easier to understand, test, and verify. A single, overly complex component is just a black box waiting for a bug to hide inside.
Right. Keep it simple.
Closely related is restricted size of interfaces. Limiting communication points between components reduces potential error vectors. Fewer connections mean fewer places for things to go wrong and fewer opportunities for unintended interactions.
So it's about making components focus and limiting how much they talk to each other. What else stands out as a critical principle for architecture?
Okay, strong cohesion within components. This means ensuring that all elements within a component are tightly related to a single, well-defined purpose. If a component does too many disparate things, its safety implications become ambiguous, hard to pin down.
So one job per component, ideally?
Pretty much. Conversely, loose coupling between components minimizes dependencies. This is often achieved via separation of concerns. It's crucial because it limits cascading failures. A problem in one component is far less likely to bring down another, preventing a domino effect.
Like that infotainment versus braking example.
Exactly. Imagine a minor issue with your car's infotainment system. If it's loosely coupled to the braking system, the infotainment glitch won't affect your ability to stop safely. But if they're tightly coupled, well, that's unacceptable.
Yeah, definitely.
Other critical principles include appropriate scheduling properties to ensure predictable execution order and timing, vital for real-time safety functions, and restricted use of interrupts, minimizing their number or using clear priorities, helps achieve determinism. Unpredictable interruptions can compromise safety-critical timing.
And what about memory and resources? How do we prevent components from stepping on each other's toes at that level?
Good question. That brings us to appropriate spatial isolation. This means keeping software components physically or logically separate in memory, preventing one from corrupting another's data. This often relies on hardware features like memory protection units or MPUs.
Hardware help?
Yes. And finally, appropriate management of shared resources. This involves implementing mechanisms, whether hardware or software, to prevent or detect conflicting access to shared resources like memory, CPU time, or communication channels. This is critical for preventing interference and ensuring that a resource-hogging component doesn't starve a safety-critical function.
So fair access.
Exactly. It's also worth noting that the standard highlights vivid examples of indicators for high complexity, things like highly branched control or data flow, too many interfaces, or excessive global variables. These are red flags.
Warning signs?
Yeah, warning signs that point to potential systematic faults that need to be addressed early in the design.
This all sounds very analytical. How are these analyses conducted at the architectural level, and what specific safety mechanisms emerge from them? It sounds like you need to find problems before they happen.
That's exactly right. This is where the proactive safety engineering really takes shape. The standard mandates conducting safety-oriented analyses at the software architectural level, drawing on principles from ISO26262-9. The purpose is multifold. Provide evidence that the software is truly suitable for its specified safety functions, identify every safety-related part of the software, and support the specification of effective safety measures.
So find the weak spots.
It's a proactive hunt for design weaknesses, conditions, or faults that could violate safety requirements before any code is even written.
And what about dependent failures? You mentioned cascading failures earlier. It seems like a perpetual concern in complex systems.
Indeed, dependent failures are a major concern, and the standard emphasizes the importance of dependent failure analysis, or DFA. The core idea is to ensure freedom from interference or sufficient independence between software components, especially when implementing different ASILs or safety mechanisms side by side.
How does DFA work?
This analysis specifically examines how a single event or fault could cause malfunctioning behavior in multiple, supposedly independent software elements. For example, a common cause failure might occur if two supposedly independent components both fail because they rely on the same faulty clock signal.
Ah, a shared weakness.
Or a cascading failure where a fault in one component propagates to others even if they are logically separate. It's about building in resilience so that a single point of failure doesn't bring down the entire safety system.
Okay, so once these analyses, the safety-oriented analysis and the DFA, identify potential weaknesses, how does that translate into concrete safety measures directly within the software architecture?
Great question. The results of these analyses directly lead to the application of specific safety mechanisms for both error detection and error handling. These are built into the architecture.
Okay, detection first. What kind of mechanisms?
For error detection, examples include range checks for inputs or outputs, ensuring a sensor value isn't wildly outside expected limits. We also use plausibility checks, perhaps by comparing sensor data to a simple reference model. Is this value even physically possible right now?
Sanity checks.
Exactly. There's detection of data errors through techniques like error detecting codes like CRC checks or storing critical data redundantly. And we implement monitoring of program execution using watchdogs or logical temporal monitoring to ensure critical tasks are running and on time. We might even use diverse redundancy.
Diverse, meaning different.
Yeah, where two different software algorithms or designs perform the same function, and if the results differ, an error is detected. It assumes they won't fail in the exact same way.
Clever. And what happens once an error is detected? How does the software safely respond to prevent a hazardous situation? What about error handling?
For error handling, the mechanisms are equally critical. Examples include deactivation to a safe state where the system gracefully shuts down to a minimal, non-hazardous configuration. Or maybe static recovery mechanisms, which could be something like a recovery block, where the software has predefined alternative code path they can switch to if a fault is detected, ensuring it can still achieve a safe state.
Plan B built in.
Sort of, yeah. We also employ graceful degradation, prioritizing critical functions while others are reduced or disabled, or using homogeneous redundancy, identical copies, for transient faults, or diverse redundancy, different designs, for systematic faults by having different software designs to fall back on. It also includes using correcting codes for data, not just detecting errors but fixing them, and meticulous access permission management for shared resources. These mechanisms are the software's active, pre-planned defenses against potential hazards.
This sounds like a lot of focus on preventing interference between components. Is there a key technique used to implement freedom from interference, specifically for software?
There is, and it's called software partitioning. It's a key technique to implement freedom from interference between different software components, especially crucial when you have components of different ASILs running on the same hardware, which is very common.
How does partitioning work?
It requires very careful use of shared resources like CPU time and memory, and often relies heavily on dedicated hardware features, especially for ASIL-D systems, where this hardware support, like those memory protection units we mentioned, is mandatory.
Okay.
Crucially, the element of the software that implements this partitioning, often a real-time operating system or a hypervisor, must itself be developed in compliance with the highest ASIL of any partition it manages.
Why is that?
Because its integrity underpins the safety of all other partitions. If the partitioner fails, all partitions can potentially fail or interfere with each other. It's the gatekeeper.
So it's about careful design, deep analysis, and then implementing specific safety mechanisms like partitioning. What else is part of this architectural design phase, particularly regarding resource management and verification?
Well, beyond the design itself and the safety mechanisms, this phase also involves making an upper estimation of required resources for the embedded software. This isn't a guess, it's a calculated estimate.
What resources?
Crucial elements like execution time, ensuring the software has enough processing power to meet all its deadlines under worst-case conditions. Storage space, both for volatile data in RAM, like stacks and heaps, and non-volatile code, and fixed data in ROM. And communication resources, making sure data can flow freely and reliably between components and with hardware, like network bandwidth.
Why is this estimation so important early on?
Because underestimating these can lead to performance degradation or even system crashes under load later in development when it's much harder to fix. You need to know you have enough headroom.
And then, once this intricate architecture is designed, it must be verified, right? How is that rigorous verification of the software architectural design carried out before any real coding begins?
Absolutely. The verification of the software architectural design is incredibly rigorous. It uses various methods to ensure the design is sound and ready for implementation. These include traditional walkthroughs and inspections of the design.
Human reviews.
Exactly. Human-centric reviews, where teams meticulously review the architectural documentation for flaws, inconsistencies, or non-compliance with principles. For more complex systems, simulation of dynamic behavior can be used to predict how the architecture will behave under various conditions, or prototype generation to test parts of the design on a non-final target.
What about more automated or formal methods?
Yes. More advanced methods include formal verification, which uses mathematical proofs to confirm specific safety properties of the design, a very powerful but resource-intensive technique often reserved for the highest ASILs. We also use control flow analysis to understand the sequence of operations within and between components, and data flow analysis to track how data moves throughout the system, ensuring its integrity. And finally, Scheduling analysis is crucial to ensure processes run predictably and meet their timing deadlines.
So a whole battery of checks.
This multifaceted approach ensures the design is suitable for meeting safety requirements, is compatible with the target environment, and adheres to all design guidelines before moving on to the costly and time-consuming implementation phase. It's all about catching errors as early as possible at the blueprint stage.
Amazing. Now, we've specified the safety requirements, designed the architecture, and verified that blueprint. The next logical step is to actually build the individual components. Let's delve into Section 4, Software Unit Design and Implementation. What are the objectives here, and how do we translate that architectural design into executable code?
Okay, implementation. The objectives here are twofold. First, to develop a detailed software unit design that aligns perfectly with the software architectural design and the allocated requirements, supporting its implementation and subsequent verification.
So designing the details of each small piece?
Exactly. And second, and this is where the physical creation happens, actually implement these software units as specified. This is where the abstract designs become tangible lines of code.
So we're talking about taking that high-level architecture and breaking it down into specific implementable pieces, the actual code modules or functions, getting down to the nitty-gritty.
Precisely. This involves detailing the functional behavior and internal design of each software unit to a level sufficient for implementation. This might mean describing the exact algorithms, the specific data structures, or the internal states of a particular function or module.
And how is this done by hand?
It can be done either through manual coding by a developer, or increasingly through automatic code generation from sophisticated models, especially in model-based development environments like Simulink or TargetLink. The goal is enough precise detail for a programmer or a machine to write the correct, safe code.
And when it comes to writing that code, whether by hand or generated, the choice of programming language and, more importantly, how it's used, must be absolutely critical for safety, right? We can't just write code any way we want.
You're spot on. It's absolutely paramount. The standard heavily stresses that applying specific design principles at the source code level is crucial for avoiding systematic faults and ensuring properties like correctness, simplicity, readability, robustness, and verifiability. This isn't just about writing code that works. It's about writing code that is inherently safe by design, resistant to common pitfalls and subtle errors.
What are some of these specific design principles, and why are they so incredibly important for safety? Give us a sense of what engineers are focused on when they code.
Sure. There's a comprehensive list of these principles in the standard, and they might seem strict, but they're there for very good reasons. For example, ensuring single entry and exit points in subprograms or functions.
Why is that important?
It greatly enhances clarity and reduces complexity. Imagine trying to debug a function that can jump in and out from multiple places. It's a nightmare, and bugs just love complexity.
Okay, keep the flow simple.
Another critical one is no dynamic objects or variables, or you need online testing during their creation.
No dynamic memory allocation. Why? That's common in other software.
Well, consider this. In a safety-critical system, you need absolute predictability. If your braking software is constantly allocating and deallocating memory on-the-fly dynamic memory allocation, you introduce an element of, well, chaos.
Unpredictability.
Right. A sudden memory allocation failure or unexpected fragmentation could stall or crash the system at the worst possible moment. That's why avoiding dynamic objects isn't just a good practice. It's a foundational principle for safety that locks down predictability, ensuring memory behaves exactly as expected. Every single time. You typically pre-allocate everything you need.
Wow, that's a deep insight into why what seems like a simple coding rule can have such profound safety implications. What about how variables themselves are handled?
A simple but powerful principle is initialization of variables. This prevents undefined behavior that could occur if a variable is used before it's given a known value, which is a surprisingly common source of bugs in any software, let alone safety critical.
Initialize everything. Got it.
Similarly, no multiple use of variable names within overlapping scopes improves clarity and avoids unintended side effects, where changing one variable inadvertently affects another part of the code because the names clashed.
Keep names unique and clear.
Another big one for maintainability and safety is avoiding global variables or strictly justifying their usage. Global variables can be modified by any part of the program, leading to uncontrolled dependencies and making it incredibly hard to track down where an erroneous value originated.
The shared whiteboard problem you mentioned.
Exactly. Chaos. And for low-level programming, particularly in C or C++, Restricted use of pointers significantly reduces the risks of memory corruption, dangling pointers, buffer overflows, notorious sources of bugs and security vulnerabilities. Pointers offer power but demand extreme care in safety-critical contexts.
These sound like best practices for any robust software, but maybe even more vital for safety. What about avoiding hidden behavior or unpredictable flow in the code?
Exactly, like no implicit type conversions. This prevents subtle data integrity issues that can arise when the compiler automatically converts data from one type to another without explicit developer awareness, potentially leading to loss of precision or unexpected values. Be explicit.
Make the conversions clear.
No hidden data flow or control flow ensures transparency and verifiability, meaning you can clearly see how data moves through the system and how execution paths are determined without any sneaky side effects or hidden dependencies. Finally, things like no unconditional jumps, like goto, promote structured programming, making the program flow easier to analyze, and no recursions prevent stack overflow issues, which can be catastrophic in safety-critical contexts where resource limits are tight and predictability is key.
So lots of rules to follow.
Many of these principles are actually embodied in widely recognized coding guidelines like MISAR AC or MISAR AC++ FISNT. These are sets of programming guidelines for using C and C++ in embedded systems, specifically designed to enhance safety, portability, and reliability by forbidding risky language features.
So MISRA is a practical application of these principles.
Very much so. They contribute directly to software robustness by preventing common programming pitfalls like implausible values, execution errors like division by zero, and critical data flow or control flow errors. It's disciplined coding.
Okay, we've designed and implemented the individual software units, paying meticulous attention to these safety principles. Now comes the moment of truth. Rigorous checks. Let's talk about software testing and verification strategies, starting with unit testing. What are its primary objectives, and what methods are used at this foundational level?
Right, testing. Unit testing is indeed the first and often most critical line of defense, focusing on individual software components, the units in isolation. Its objectives are to provide concrete evidence that the software unit design and its implementation satisfy their specific requirements, that safety measures are correctly implemented within that unit, and crucially, that the unit contains no undesired functionalities.
So, verifying that the smallest building blocks are sound and behave exactly as expected alone. How is that achieved, particularly with the rigor required for functional safety?
There are a variety of robust verification methods used. We start with reviews and analyses such as code walkthroughs, pair programming, and formal inspections, especially critical for higher ASOLs like C and D. These are human-centric checks to spot logic errors or guideline violations early.
The human eye is still important.
Absolutely. Then there's semi-formal and formal verification, which can use mathematical models and proofs to confirm the correctness of algorithms or properties, particularly for the most critical units or highest ASOLs.
And automated tools.
Yes, beyond human review, static analysis is incredibly powerful. This includes static code analysis, where automated tools search the source code for known faults, potential bugs, or check adherence to coding guidelines like MISRC, all without actually running the code.
Finding errors without running the code, that's fascinating.
It is. And more advanced static analyses, often based on techniques like abstract interpretation, can detect complex issues like potential data type problems, uninitialized variables, race conditions between tasks, or even deadlocks, all identified before the software ever executes on hardware. It's an astounding capability for catching subtle issues.
Okay, static checks are powerful, and then, of course, actual dynamic testing, running the code. What does that involve at the unit level?
Right, dynamic testing is where the code actually runs, usually in a specialized test harness. Requirements-based tests verify the unit against its specified functional requirements, making sure it does what it's supposed to do for given inputs. Interface tests ensure data integrity at the unit boundaries, checking that inputs and outputs are handled correctly when the unit interacts with, well, the test harness simulating its neighbors.
Makes sense. Test the function, test the connections. What about this fault injection you mentioned?
Yes, fault injection testing. This is particularly powerful and may be surprising for safety. Here, we intentionally introduce faults, for example, corrupting variable values passed into the unit, or even computationally mutating lines of code within the unit to assess the unit's response and the effectiveness of its built-in safety mechanisms.
Like stress testing it with bad data or simulated bugs?
Exactly. It's like stress testing a bridge by deliberately sending a massive overweight truck over it to see if it holds up or fails gracefully. We also perform resource usage evaluation to check execution time and memory consumption, ideally on the final target processor or a very close simulation, to ensure it meets performance needs.
And for model-based development?
For model-based development, back-to-back comparison tests are crucial. You compare the behavior of the original model against the behavior of the automatically generated code running on a target or simulator, using the same test inputs. The output should match, proving the code generation was accurate.
How are the actual test cases derived for unit testing to ensure comprehensive coverage? You can't test everything.
No, you can't test every possible input, so test cases are systematically created using several methods to get the best coverage. We perform an analysis of requirements to derive tests directly from the specifications, what should it do. Then we use generation and analysis of equivalence classes.
Equivalence classes?
Yeah, it means dividing the possible inputs and outputs into groups or classes where the behavior is expected to be similar. You test one representative value from each class, assuming it covers the others. It avoids redundant tests.
Hard.
Then there's analysis of boundary values, testing at and around the limits of input ranges like minimum, maximum, just inside, just outside. Errors often lurk at these boundaries. And finally, error guessing, which relies on the experience of engineers to anticipate common pitfalls or areas where faults might likely occur based on the code's complexity or past issues.
Experience counts. And how do we know if our testing is complete enough? What about test coverage? That sounds important.
Test coverage is absolutely crucial for evaluating verification completeness. It's not enough to just run tests. You need to measure how much of the requirement and the code was actually exercised. It involves determining requirements coverage, making sure every single requirement has at least one corresponding test case that passes.
Okay, covering the specs, what about the code itself?
And then measuring structural coverage. Structural coverage metrics ensure that the code itself has been sufficiently exercised by the tests. This includes statement coverage. Was every line of code executed at least once? Branch coverage. Was every decision point in the code, like an IF statement, executed for both its true and false paths?
Going deeper.
And for higher ASILs, the standard strongly recommends MCDC, Modified Condition Decision Coverage.
MCDC?
Modified Condition Decision Coverage. It goes deeper than branch coverage by ensuring that each individual condition within a complex decision, like IF, A or B, ADC, has been shown to independently affect the decision's outcome during testing. It's quite rigorous, but very effective at finding bugs in complex logic.
And if you can't reach full coverage?
If coverage metrics are insufficient, say only 95% branch coverage, a rationale must be provided and justified. Perhaps it's due to dead code that can never be reached, or code intended for different configurations that aren't relevant for this specific test build. You have to explain why it's okay.
Finally, where does unit testing take place? On a developer's machine or something more specialized?
The test environment is critical. It must be suitable for achieving the objectives, considering how closely it mimics the final target environment. This could range from model-in-the-loop, MIL, where you test the software logic in a simulation environment even before code exists.
Testing the model.
Software-in-the-loop, SIL, testing the actual source code compiled for the host machine in a simulated environment. Processor-in-the-loop, PIL, testing the compiled code on the actual target processor but still in a simulated system context. Or maybe even early tests on hardware-in-the-loop, HIL, though that's more common for integration.
So lots of in-the-loop options.
Yeah. And crucially, if testing isn't on the final target hardware environment, any differences in the source code behavior, object code generated by the compiler, or the execution environments themselves must be analyzed. Additional tests might be needed to bridge those gaps, ensuring that the test results are truly representative of how the code will behave in the car.
Once individual units are solid, the next step is to integrate them, put them together. This leads us to software integration testing. What are its objectives, and how does it differ from unit testing?
Right, software integration testing. Its objectives are to define the integration steps, verify the implemented safety measures that span across units, those from the architectural level, and provide evidence that the integrated software units and components meet their architectural design requirements.
So checking how they play together.
Exactly. Unlike unit testing, which isolates individual pieces, integration testing is all about checking how these pieces interact and work together to form larger components and eventually the full embedded software. It's where you uncover issues caused by unexpected interactions between modules, interface problems, timing issues, data corruption across boundaries.
So it's about checking the connections and interactions between components layer by layer as you build up the software. What's the systematic approach to this integration itself?
The integration approach defines hierarchical steps. You don't just dump all the code together at once and hope for the best.
Big bang integration, usually bad.
Usually very bad, yes. Instead, you integrate software units into components in a defined sequence, and then those components into the full embedded software, always considering functional dependencies and, importantly, hardware-software integration dependencies. For example, you might integrate the sensor reading unit with the data processing unit first, verify their interaction thoroughly, and then integrate that larger component with the decision-making logic. It's a methodical, step-by-step assembly and test process.
And the verification methods used during integration, are they similar to unit testing but applied at this different scale?
Yes, many are similar but applied at the integration level, focusing on the interactions. We use requirements-based tests to confirm the integrated software meets its architectural requirements. And interface tests are particularly critical here to ensure robust data integrity at the boundaries between units. Are they passing data correctly? In the right format? At the right time?
Checking the seams.
Precisely. Fault injection tests are still vital, often specifically used here for freedom from interference verification checking if a fault deliberately injected into one component improperly affects another, confirming that partitioning or other separation mechanisms are working.
Testing the firewalls again.
Right. We also continue resource usage evaluation. Does the integrated code still meet timing and memory budgets? Back-to-back comparison if integrating model-based components, and control data flow verification and static code analysis run on the integrated code base. These methods confirm compliance with the software architectural design and the HSI specification, verifying specified functionality and properties across integrated components.
And test case derivation and coverage for integration, do those also scale up from unit testing, looking at the architecture level?
They do. Test cases are systematically derived using analysis of requirements, now architectural requirements, equivalence classes, boundary values, and error guessing, just as with unit testing. For test coverage, the focus shifts to evaluating requirements coverage and structural coverage, but now at the software architectural level.
What metrics are used there?
The key metrics here are function coverage, what percentage of the defined software functions or subprograms were executed during testing, and call coverage, what percentage of the possible calls between these functions were executed. This ensures all the intended architectural pathways have been exercised. Again, if coverage is insufficient, a clear rationale is required. It's about ensuring the integrated system's architectural elements have been fully exercised.
It seems like preventing unintended functionality is a continuous theme throughout the process. How is that handled specifically at the integration level when you're putting pieces together?
It's a very important point, yes. It must be verified that the embedded software intended for production includes all specified functions and only other unspecified functions if they demonstrably do not impair any safety requirements.
So no leftover secret code?
Essentially, yes. This means no leftover debugging code, for instance, that could potentially be activated accidentally in the field, unless it's absolutely guaranteed to be deactivated and doesn't impact safety or performance in any way. Any code that is not part of the final specified functionality must be justified as harmless or, preferably, removed entirely.
Clean code.
Clean intended code. The test environment for integration testing also remains critical, using SIL, PIL, or HIL, and requiring careful analysis of any differences from the final target environment to ensure that the test results are representative of real-world performance.
Now we're approaching the summit of the V model, the final validation of the software in its actual target environment. Let's discuss embedded software testing. What's the ultimate objective here, and why is this the pinnacle of verification?
This is truly the ultimate proof, the final exam before release. The objectives of this phase are to provide undeniable evidence that the entire embedded software fulfills all its safety-related requirements when executed in the actual target environment, meaning the real ECU hardware in a realistic simulated or actual vehicle setting, and contains neither undesired functionalities nor undesired properties.
So does it work safely in the real world or as close as we can get?
Exactly. It's the closest you get to real-world validation before actual deployment in a production vehicle.
And what are the suitable test environments for this crucial final stage? It sounds like they have to be very realistic.
Yeah, absolutely do. The most suitable environments include hardware-in-the-loop, HAL setups. These are sophisticated rigs that simulate the vehicle's entire environment, sensors, actuators, network traffic. While the actual electronic control unit, the ECU, running the final software, is connected and tested.
Testing the real brain in a simulated body.
Precisely. This allows for rigorous, repeatable testing of the ECU's reactions to complex, potentially dangerous real-world scenarios without putting a physical vehicle or driver at risk. Then there are electronic control unit, ECU network environments, such as test benches that integrate multiple ECUs or even the entire vehicle's electrical system, sometimes called lab cars or mule vehicles, which are actual vehicles but used strictly for testing within a controlled lab environment.
And finally,
And for the highest level of validation, testing is ultimately conducted in actual vehicles on proving grounds, test tracks, or sometimes even controlled public roads under very strict safety protocols, of course.
what testing methods are primarily used at this embedded software level? Is it still requirements-based?
Yes, the core method is still requirements-based test, confirming the software meets its specified safety requirements in this real-world context, responding accurately to realistic inputs and scenarios. But importantly, fault injection tests are used here too, but often at a different, more systemic level.
Yeah, so
For example, by corrupting calibration parameters stored in memory, simulating hardware faults like a sensor failing, or introducing errors onto the vehicle network, like CAN bus messages being lost or corrupted, in the actual embedded software environment. The goal is to see how the entire system reacts.
it's testing the system's resilience.
Exactly. It tests the overall system's resilience and its ability to maintain safety even when components, data, or communications are compromised in the target environment. It goes beyond just testing the code itself. It's testing the integrated software system's safety behavior.
How are test cases derived for this final stage? It sounds like they would need to be incredibly comprehensive to cover all real-world possibilities.
They are indeed very comprehensive. Beyond the methods used in earlier stages like analysis of requirements, equivalence classes, boundary values, error guessing, this stage also critically includes analysis of functional dependencies across the entire system. How does braking interact with stability control?
Oh.
And most importantly, analysis of operational use cases.
Operational use cases, like
Yeah.
driving scenarios.
Yes, but also covering the software's entire life cycle in the vehicle. For example, specific use cases might include: how does the software handle an over-the-air update safely while the car is parked? Are the bootloader integrity checks robust enough to ensure the main application only starts if its integrity is confirmed every time the car starts?
Things beyond just driving.
Absolutely. We also test safety-related behavior in various vehicle modes. During startup, during specific diagnostic modes used by technicians, in degraded operation, limp home, during power-down sequences, during calibration procedures, or even specific end-of-line test modes used by production personnel on the assembly line. It covers the entire operational life cycle of the software in the vehicle, accounting for every conceivable state and interaction.
And the evaluation of the results at this final stage.
Yeah.
Pass-fail.
Evaluation of results is paramount and detailed. It involves meticulously checking compliance with expected outcomes defined in the test cases and ensuring comprehensive coverage of all software safety requirements, including verifying behavior across the extensive configuration and calibration ranges that might be applied to the software in different vehicle variants. It's the final exhaustive check to sign off on the software safety before it goes into mass production.
So we've talked about fault injection testing at unit, integration, and embedded software levels. Can you maybe synthesize how this fault-based testing strategy works across these different levels? It sounds like it's much more than just finding bugs. It has a consistent, overarching goal.
You've hit on a critical point there. Fault injection testing is a consistent, critical thread woven throughout all verification levels, but its application definitely evolves.
How does it evolve?
Okay, at the unit level, it's primarily about directly manipulating the software unit itself, like corrupting incoming variables or computationally introducing small code mutations, to verify its internal robustness and the effectiveness of its localized safety mechanisms, ensuring that single module is resilient on its own.
Okay, testing the building block strength.
Then, at the software integration level, fault injection often targets the interfaces between components or specific architectural safety measures like memory protection. Here, it's used to rigorously verify freedom from interference, confirming that a fault in one component doesn't inadvertently affect another in an unsafe way, and that safety mechanisms designed at the architectural level, like error handlers, are truly implemented and effective.
Testing the connections and architectural defenses.
Right. Then finally, at the embedded software level, it moves to manipulating system parameters or simulating external faults in the actual hardware environment. Think corrupting calibration data, simulating sensor failures, messing with network messages. This tests how the overall system reacts to these faults and if its complex safety mechanisms involving both hardware and software working together effectively detect the fault and mitigate the hazardous situation, maybe by transitioning to a safe state.
So the consistent goal here isn't just to find obvious bugs, but something deeper related to proving safety. It's about proving resilience.
Precisely. Its consistent goal across all these levels is to proactively assess the software's resilience against various types of faults, both potential random hardware faults manifesting in software and potential systematic software errors missed earlier, evaluate its response to these faults, and definitively confirm the effectiveness of the designed safety mechanisms. It's about proving that the software and the system it controls will react safely and predictably even when things inevitably go wrong. It's a crucial proactive measure, not just a reactive bug hunt, building confidence in the failure modes.
It brings us to another fascinating aspect that often gets overlooked. Ensuring trustworthiness, not just in the code itself, but in the tools and components used to create it. Let's talk about software tool qualification. Why is this even necessary in the first place? Don't we just trust our compilers?
That's a vital point that often surprises people outside the functional safety world. We can't just implicitly trust them for high ASIL applications. The tools used in the software development and verification process, things like compilers, linkers, code generators, static analyzers, debuggers, testing frameworks, even requirements management tools, are themselves software and potential sources of systematic faults.
The tools can have bugs too.
Exactly. If a compiler, for example, has a subtle bug in its optimization routines, it could potentially introduce errors into your safety-critical code without you or your engineers ever realizing it, because the error isn't in your source code logic, but in the way the tool translated it into machine code. For safety-related development, confidence in these tools is absolutely paramount.
So how does the standard ensure this confidence in the tools themselves? What does qualification actually mean for a software tool? How do you qualify a compiler?
Good question. The standard requires objective evidence of qualification for tools whose failure could impact safety. Conceptually, this involves rigorously evaluating their suitability for the specific safety application and demonstrating, with evidence, that they don't introduce unacceptable errors into the safety-critical software or that any potential errors are detected.
What kind of evidence?
There are several methods allowed, depending on the tool's complexity and the required tool confidence level. You might rely on extensive operational experience, basically collecting documented evidence that the tool has been used successfully and without known safety-relevant problems in similar safety-related projects over a significant period.
Proven in use.
Or you could perform validation of the tool itself, perhaps by running specific test suites, like compiler validation suites, through the tool to ensure it performs as expected for safety-relevant functions and doesn't miscompile critical constructs. Another approach is using a tool that was developed according to a safety standard itself.
A certified tool.
Right, or having an independent assessment of the tool, perhaps by a certification body like TOO, to vouch for its reliability and suitability for a given ASIL. Especially for complex tools like code generators used in model-based development, the reliability of automatically generated code hinges on the confidence in the code generator. A qualified tool helps mitigate the risk of the tool itself injecting coding errors. The choice of method depends on the ASIL of the software being developed and the potential impact of a tool failure.
That makes perfect sense. If your tools are faulty, then the code they produce or verify might also be faulty. Now, what about software component qualification? Automotive software often reuses existing components, right? Maybe from other projects or third parties. How do you trust those if they weren't built to ISO 26262 from the start?
That's a huge aspect of modern automotive development, absolutely. Efficiency often relies on reuse. Road vehicle software frequently reuses existing software components, and crucially, these might not have been initially developed under the strict ISO 26262 standard. Think of basic software like real-time operating systems, RTOS, communication stacks like CAN or Ethernet drivers, libraries, or pre-existing architectural elements.
Stuff you might buy or inherit.
Exactly. When these are used in a safety-related application without modification, or sometimes even with modification, they must be qualified if they implement safety requirements.
So how does that qualification process work for reusable components? It sounds like you're building a bridge of trust for something not originally built to the same safety standard.
That's a good way to put it. Qualification is the process of providing sufficient evidence that these pre-existing or reusable components are suitable and reliable for use in a specific functional safety context, ensuring they can meet the assigned ASILs and safety requirements within that context. This process allows their integration into safety-critical systems while maintaining the overall functional safety integrity of the item.
What kind of evidence works for component qualification?
The evidence for qualification can come from several sources, and often a combination is needed. You might do an analysis of the existing development process that was used for the component, comparing it retrospectively against ISO 26262 requirements to see how well it aligns.
A process gap analysis.
Right. Or you might develop a safety case specifically for the component, explicitly arguing why it's safe enough for this particular new application based on its design and history. Extensive testing results of the component, both in isolation and integrated into the target system, are almost always required. You might rely heavily on proven-in-use arguments based on documented positive field experience, showing proof of the component's reliable performance in previous similar applications over millions of miles or hours.
Track record matters.
It does, but it needs solid data. Sometimes, modification of the component is necessary to add specific safety mechanisms or wrappers around it, followed by full verification of those changes, according to ISO 26262. This rigorous process is about transforming a general-purpose or pre-existing component into one that is demonstrably safe and reliable enough for use in a life-critical automotive application. It's a critical enabler for efficiency, absolutely, but it comes with significant due diligence and responsibility. You can't just assume it's okay.
We've covered a tremendous amount of detail about ISO 26262 Part 6, from requirements through architecture, coding, testing, and even qualifying tools and components. Let's maybe zoom out for a moment and really put it into perspective. What's the bigger picture here? What's software's overarching fundamental role in functional safety for our vehicles?
The central message, which we really cannot reiterate enough, is that software plays an absolutely critical, pivotal role in avoiding and controlling systematic failures that could lead to hazardous situations in road vehicles. With the incredible exponential increase in technological complexity and the staggering amount of software in modern cars, we're talking hundreds of millions of lines of code now in some high-end vehicles, the risks from systematic software failures have also increased dramatically.
More code, more potential problems.
Exactly. It's the software that enables the complex safety functions we increasingly rely on, from advanced driver assistance systems, ADS, like automatic emergency braking and lane keeping, to fundamental vehicle control, like electronic stability control, braking, and steering systems. It is truly the unseen guardian, not just controlling functions, but ensuring the safety and reliability of that control under all conditions.
So it's not just about what the hardware can do, but how the software orchestrates it safely and reliably, making the hardware perform its safety-critical duties correctly and predictably.
Precisely. The entire rigorous development process we've just detailed in Part 6, from defining precise software safety requirements derived from system needs, to meticulous architectural design focusing on robustness and isolation, secure implementation following strict coding principles, and multi-layered exhaustive testing, including fault injection, is absolutely fundamental to achieving overall functional safety for the vehicle. This framework provides the necessary requirements, processes, and methods to mitigate these systematic software risks, ensuring that those high-level safety goals for the vehicle are actually realized reliably in every single line of relevant code.
And it connects back to those specific safety mechanisms.
Directly. It connects directly back to the specific safety measures and mechanisms implemented directly in software, such as the error detection and handling strategies we discussed earlier, and ensuring freedom from interference between software elements using techniques like partitioning. All these things prevent a minor bug or a single hardware fault from escalating into a catastrophic system failure.
So it's a comprehensive end-to-end approach, not just isolated coding or testing. What other elements are crucial beyond the code itself? It sounds like the overall process, environment, and collaboration are key.
Absolutely. Beyond the code itself, the process is paramount. A suitable and consistent software development lifecycle process and a supportive development environment are absolutely essential. The standard emphasizes this. It also acknowledges that advanced approaches like model-based development, MBD, which uses graphical models to design algorithms and often automatically generate code, and configurable software, which allows for different features or parameters to be activated or deactivated based on vehicle options or markets, bring significant efficiency benefits.
But they have their own challenges.
Exactly. They also introduce specific safety considerations that must be carefully managed. For example, ensuring the automatically generated code from a model is truly safe, efficient, and adheres to all coding principles, and rigorously verifying the configuration mechanisms.
And what about how cars are actually built today? It's rarely one company doing everything.
That's another critical point. In today's globalized automotive world, where different suppliers might be developing different ECUs or software components, collaboration and clear interfaces are vital. The standard explicitly acknowledges the reality of distributed development and the concept of safety elements out of context, or COOC,
EOS.
safety element out of context, where components like maybe an airbag ECU or a generic sensor fusion library might be developed by a supplier without the full context of the final vehicle it will be used in.
That sounds risky.
It requires very careful management. Part 6, and the standard overall, stresses the absolute need for clear documented agreements. Development Interface Agreements, or DIAs, defining the scope, methods, interfaces, assumptions, and shared responsibilities for safety analyses and verification among all participating organizations in the supply chain. Functional safety cannot be a siloed activity done by one group.
It has to be integrated everywhere.
It's intricately woven into common function-oriented and quality-oriented activities and work products throughout the entire product lifecycle, from the initial concept phase through development, production, operation, service, and even eventual decommissioning of the vehicle. It's a shared responsibility across the entire ecosystem.
What an incredible journey into the world of automotive software safety. We've really peeled back the layers on ISO26262-Part 6, revealing the incredible depth and, frankly, the precision required for product development at the software level.
It's definitely demanding.
From the initial derivation of safety requirements all the way down from the system, to the meticulous architectural design, the disciplined implementation with safe coding rules, and then the exhaustive multi-stage testing, every single step is a testament to the unwavering commitment to safety in our vehicles.
And hopefully, you now have a more profound understanding of how software acts as that unseen guardian in our vehicles. It's not just enabling cool features, it's actively preventing hazardous situations and ensuring the reliability of critical systems that protect lives.
It truly is a world where every line of code matters, every interface is scrutinized, and every process is designed with safety as the ultimate destination.
That sums it up well.
So here's a final thought to maybe mull over as you drive away from this deep dive. Looking ahead, as vehicles become even more intelligent, incorporating advanced AI and machine learning for perception, decision-making, and control.
A huge trend.
And as automated code generation becomes even more sophisticated, maybe even generating novel solutions, how might these innovations further revolutionize and perhaps challenge the rigorous safety standards and processes like those in ISO 26262-Part 6 that we've explored today?
That's the billion-dollar question. How do you verify and validate systems that learn and adapt, potentially in unpredictable ways?
Exactly. And what new verification and validation paradigms will need to emerge to meet these evolving complexities, ensuring we can still build trust in systems that might learn and adapt dynamically. It's a fascinating and slightly daunting future to consider for automotive safety.
It certainly is. The principles will likely remain, but the methods will have to evolve significantly.